Hello. In this and the next few videos, I'm going to be giving an overview of Cool, the programming language for which you'll be writing a compiler.
Cool is the classroom object-oriented language, and the acronym, of course, is COOL. And the unique design requirement for Cool is that the compiler has to be able to be written in a relatively short period of time. We only have 1 quarter, or in some cases a semester, for students to write the compilers. And so Cool has to be implementable quickly. And actually, since it's used primarily for teaching compilers, the number of Cool compilers in the world vastly exceeds the number of Cool programs. So there are many, many more compilers have been written. Thousands of compilers, maybe tens of thousands of compilers have been written for Cool, but probably only some dozens or hundreds of Cool programs. And so it's probably the only language in existence for which this is true, that the number of compilers actually exceeds the number of programs. But it does tell you about the main design requirement. It's much more important in Cool that the compiler be easy to write than that it be easy to write programs in. And so there are some quirks in the language, things that have been done specifically to make it easier to implement, where that wouldn't take away from the teaching value of the language, but that would make it inconvenient to use the language on a day-to-day basis as a working programmer. So what is in the language? Well, we've tried to design it so that it will give you a taste of modern notions of abstraction, static typing, reuse through inheritance, automatic memory management, and there's actually a few more things that we'll talk about when we come to them. But many things are left out. We're not going to be able to put everything in the language and have it be implementable quickly. We'll be able to cover some things in the lectures, but unfortunately there'll even be some interesting language ideas that we won't be able to get to in this class. So the course project is to build a complete compiler, and specifically you're going to compile Cool into MIPS assembly language. So MIPS is a real instruction set. It was for a machine that was designed in the 1980s, and there is a simulator for MIPS that runs on just about any kind of hardware, and so this makes the whole project very portable. We can run your compiler, you can generate MIPS assembly language, and then that MIPS assembly language can be simulated on just about whatever kind of machine you have access to. The project is broken up into 5 assignments. First, you're going to write a Cool program, and that program itself will be an interpreter to give you a little bit of experience with writing a simple interpreter. And then the compiler itself will consist of the 4 phases that we discussed: lexical analysis, parsing, semantic analysis, and code generation. And all of these phases, I should emphasize, are plug compatible, meaning that we have separate implementations, separate reference implementations of each of these. And so, for example, when you are working on semantic analysis, you'll be able to take the lexical analysis, parsing, and code generation components from the reference compiler and plug your semantic analysis into that framework and test it against the reference components. And so this way, if you have trouble with one component, or aren't sure that one of your components is working very well, you won't have a problem in working on a different component because you'll be able to test that independently. And finally, there's no required optimization assignment, but we do have some suggestions for optimizations that you can do, and many people have written optimizations for Cool. And so this is an optional assignment if you're interested in learning something about program optimization.
So let's write the simplest possible Cool program. And the first thing to know is that Cool source files end in the extension .cl for Cool, and you can use whatever editor you like to write your programs. I happen to use Emacs. You can use some other editor if you like. And every Cool program has to have a class called main. And let's talk about that for just a second. So a class declaration in Cool begins with the keyword class, followed by the name of the class, so in this case main, followed by a pair of curly braces. And inside the curly braces is where all the stuff that belongs to the class goes. And every class declaration must be terminated by a semicolon. So a program consists of a list of class declarations, each class declaration terminated by a semicolon. So that's the structure of a class. And now we need this class to actually do something. So we're going to have a method in this class, and let's call the method main. In fact, the main method of the main class must always exist. This is the method that's run to start the program. And furthermore, this method must take no arguments. So the argument list for the main method is always empty. And let's say the main method, its body always goes in a pair of curly braces. So the main method always goes inside curly braces. And a class consists of a list of such declarations. And again, those declarations must all be separated by semicolons, or terminated, excuse me, by semicolons. So in this case, we only have one method in the class, but it still has to have its semicolon. And now we can say what we want the method to actually do. So this is the place where the code for the method goes. And let's just have the simplest possible method, the one that just evaluates to the number 1. Okay? So cool is an expression language, which means that wherever a piece of code can go, you can put an arbitrary expression. Any expression can go there. There's no explicit return statement for a method. It's just the value of the method body is the value of the method. So in this case, we just put the number 1 in there, and that will be the value of this method when we run it. So let's save that. And now we can try compiling this simple program. So how do we compile? The compiler is called coolc for the cool compiler. And you just give the cool compiler a list of cool source files. So in this case, there's just one file, 1.cl. Hit enter, and we got a syntax error. So we have to come back and fix that. And the error says that at or near the open curly brace on line 3, there is a mistake. And I know what the mistake is because I'm a competent cool programmer, at least somewhat competent cool programmer. Cool methods must declare their return type. So we need to put a type here, and the syntax for the declaration is to put a colon after the name of the method in the argument list, and then the name of a type. And since we're returning the number 1 for this for this method, we might as well say that the main method is going to return an integer. So save that, go back over to our compilation window, and let's compile the program again. And this time it compiled successfully. And now if we look in our directory, we see that there is a new file called 1.s. That's the assembly code for the program 1. And now we could try to run this code. And the MIPS simulator is called SPIM, and it just takes a assembly file to simulate. And so we just give it 1.s, hit enter, and it'll run. A whole bunch of stuff is printed out. But as you can see, it says partway down that the cool program successfully executed, so that's good. And then afterwards there are some statistics and things like the number of instructions executed, the number of loads and stores, number of branches. Those things would be interesting if we're worried about performance, if we were, say, working on the optimization of the compiled code. But we're not doing that right now. We're just running programs, and we can see that this program worked. So the program ran, it terminated successfully, but it didn't actually produce any output, and that's because we didn't ask it to produce any output. If we want to have output, we'd have to go back and modify the program again. So what this program does currently is it just returns this value, but nothing is done with that value. It's not printed out or anything like that. If you want to have something printed out in a cool program, you have to do that explicitly. So there's a special class built in, a primitive class called IO, and we can declare what's called an attribute of this class. There'll be an IO attribute, and it'll be called I. Okay, and I will be an object that we can use to do IO. So now in our main method here, we could add a call to outstring. I.outstring is how we invoke a method. Okay, so outstring is a method of the IO class, and so we use I to invoke that method, and then we can pass it a string that we want printed out on the screen. So for example, we could say hello world. Okay, and now we have to decide what to do with our number 1 there. And let me show you one more feature of cool. Let's leave the 1 there and let's make it part of a statement block. So a statement block consists of a sequence of expressions separated by semicolons. And you can have any number of expressions, and the semantics of a statement block or an expression block is to just evaluate the expressions in order, and the value of the block is the value of the last expression. And now a statement or an expression block has to be included in its own set of curly braces. Okay, so that now is a valid cool program. So let me just read this for you. So the body of the program is a block of expressions. The first one executes a outstring call to the object I, which is going to print hello world for us. And then the second one evaluates to 1, which is the value of the entire method. Okay, actually I should say it's the value of the block. Okay, and then because the block is the body of the method, the value of the block becomes the value of the entire method. So 1 will be returned from this method call. So let's save this. Go back over here and let's compile this again. So it looks like I failed to save it. Let's compile this and we see we have a syntax error. And so it says on line 4 we have a syntax error at or near our closing curly brace. And the problem here is that a statement block or an expression block consists of a series or a sequence of expressions terminated by semicolons, and we forgot to terminate the last expression in the sequence by its semicolon. So we have to add that. And now we should be able to compile this. And lo and behold, it compiles correctly. And then we can run it. And now we see, oh, we got another mistake. So we have on, when the program ran, it complained that we have a dispatch to void. So that on line 4, our dispatch was to an object that didn't exist. And you can see the dispatch call right here to I, and it doesn't exist because, in fact, we forgot to allocate an object for I. So here we declare I to be of type IO, but that doesn't actually create any objects. That just says that it just creates a variable name I, but I doesn't actually have a value. So if we want I to actually have a value, we have to initialize it to something. So we can initialize it to a new IO object. And new here is the way that you allocate new objects in cool, and new always takes a type argument. So in this case, we're creating a new object of type IO, and we're assigning it to this object I. And notice here that I is what would be called a field name in Java. It's what we call an attribute in cool. So so these are the data elements of the class, and so the class can have both names of things that are attributes or fields that hold values, as well as methods that can perform computation. So let's save this and switch back. And now we'll compile this again. So, and it still compiles, and now we can run it. And now it runs, and lo and behold, as you can see down there, third line from the top, it prints out hello world. And that looks a little bit ugly because the successful execution message is on the same line as our hello world message. So let's fix that. Let's come back over here, and in our string here we can add a new line. Okay, at the end of the string. So \n is how you write a new line character in a string. Save that, come back over here. Let's compile. So if you don't know Unix, bang will repeat the previous expression, the previous command that began with the same prefix that you type after the bang. So I want to run the last command that began with C, which is to compile. And then I want to run the last command that began with S, which is to run spim. And now we can see, there it is, all nice. Hello world is on a line by itself. So let's continue now. Let's clear all this out. So now let me just show you a few variations on the same program. What I'm going to do here is just rewrite it in a couple of different ways, just to illustrate a few features of cool, and get you more familiar with the syntax, and also just show some alternative ways to do the same thing. So, this block here of expressions is kind of a clumsy way to implement the Hello World program. So let's get rid of that. Let's get rid of the block. Let's get rid of the one here at the end. Okay, let's just make the statement body a single expression again. And now the problem we're going to have is that the types won't match. But just to illustrate that, let me show it to you. So let's do cool C of 1.cl. And you'll see here that it complains that the inferred return type IO of the method main does not conform to the declared return type int. So coming back over here to the program, the compiler figured out that this expression, i.outstring, yields an object of type IO. So it returns the I object as the result of evaluating this expression. And that does not match the type int. And so naturally, the compiler says, hey, something's wrong with the types. Well, that's easily repaired. We can just change the return type of the main method to say it returns something of type IO. So let's go back over here and see that that now works. Oops. So we compile the program, and then we run spim on the output, and yes, everything still works as expected. Now, we don't have to be so specific about the type over here, since we're not actually using the result of the method body for anything. I mean, the program just exits once it prints the string. We could have allowed ourselves more flexibility here. We could have just declared the result type of main to be of type object. So object is the root of the class hierarchy in cool. Every other class is a subclass of object. So let's come back over here. Let's save this first, and then we can come back over to our compilation window. We can compile it, and we can run it. And it still works. So now, another thing we can do if we want is we could observe here that this attribute that we declare, this field I, isn't really necessary. Here we allocate, we have the special name I. When the main object is constructed to run the program, a new IO object is allocated to I, and then that gets used in the main method. We can actually just do all of that inside the main method itself by just allocating a new IO object right here, and then calling outstring on that object. All right, so this should also work. And let's check it out. So it compiles, and lo and behold, it runs. All right, so coming back over here, let's illustrate one more, or a couple more things that we could do. So we could also say that class main inherits from IO. So we have to have the IO functionality somewhere in order to call the outstring method. So we've been doing that by creating a separate object of type IO. But now we could say, well, just the main object is itself something that has all the capabilities of IO by inheriting from IO. And if you've seen any object-oriented language before, this will be a familiar concept. So main here gets all the attributes and methods of IO in addition to whatever attributes and methods of its own that it will have. And now, instead of having to allocate a new IO object in order to call outstring, we can just invoke it on self, which is the name of the current object when the main method runs. In other languages, self is called this. Okay, and so we saved it. So now let's go over and compile this. So it compiles, and it runs. All right. So last example here. We don't have to name self actually in this dispatch. So there's a feature that allows us to call a method without explicitly naming the object on which it's dispatched, and that defaults to self. So if no object is named in a dispatch, then it's just a dispatched self. So this should also work, and indeed it does. So that concludes our first example. In the next couple of videos, we'll look at some more complex examples of cool programming. Welcome back. In this video, we're going to look at another example of cool programming. This time, let's move beyond the simple hello world kind of examples and on to something more exciting, say the ever popular factorial function. So, in order to write factorial, we'll need to open up a file in which we can write some code. Let me start that. And recall from last time that every cool program has to have a main class, and the main class is required to have a main method. And we don't care what the main method returns, so we'll just have it return something of type object. And let me just fill in the skeleton here of the file. And so now we're ready to write some code. So what are we going to have the main method do? Well, before we can actually write factorial, before we can get to the guts of this program, which is actually not very difficult, we need to talk about I/O some more, because we're going to need to be able to read and write numbers. We're going to be able to read numbers from the user who's running the program and print them back out. So let's just review a little bit about I/O. So in order to invoke the I/O functions, we need an I/O object. And one of the I/O functions is something that prints out a string. So let's just write a program that we already know how to do, just to confirm that we remember that. And now we can compile this program, and it should just print 1. And let's see, indeed it does. Okay, so it prints out the number 1. And so now let's come back here and let's talk about how to do input. So instead of just printing out the number 1, let's print out a string that the user types in. So in here, we're going to read a string. And in order to do that, we need an I/O object because there is another function, another method called inString. Okay? And so this will read in a string and return a string. And then to make sure that we get the nice output, let's concatenate onto that string a new line. So this is just to, when it prints the string back out, it'll be printed on its own line. So let's try compiling this. And mistake. It compiles, and now we can run spim. Remember, the bang command in Unix runs the previous command that began with the same letters. And now the program runs and it waits because it's waiting for me to type something. And if I type in 1, it prints back 1. And if I type in 42, it gives me back 42. All right, so now the next thing we need to talk about is how to convert strings into integers, because if we're going to do factorial, we want to work on integers and not strings. And at the moment, we're just reading and writing strings. So there is a library written in Cool that does conversion between integers and strings. And we're going to give the main class here the functionality of that class, which is called A2I for ASCII to integer. And that defines a bunch of methods that can convert between strings and integers. So let's add those commands in here. So here, here's our string that we've read in. And what we want to do now is to convert this into an integer. So let me just add a couple of parens here. So there's our string. Okay. And now we're going to invoke on that the method, we're going to call on that the function, the method A2I. Okay, and let's just double check here that we've got parens in the right place. So that's the argument to A2I. Now recall that when we have a dispatch to a method and it's just sitting by itself with no object, it's a dispatch to the self object. And the self object is the object of the current class that we're in this case, the main object, which has inherited the A2I methods. And so the A2I function should be defined in there. Now we have an integer, and we can do something with that integer if we like. So let's add some more parens here. And let's say we just add 1 to the integer. Okay. And then once we're done with our integer, whatever operation it is that we want to do on the integer, we need to convert it back to a string so that we can print it out. And there's an inverse function, I to A, that will do that. So I don't know if we have all the parens in the right places at this point. So let's just check. Yes, that looks like that should work. So this will read in a string, convert it to an integer, add 1 to it, convert it back to a string, concatenate on a new line, and print it out. And let's see if all that actually works. So let's run the compiler, and we got a problem here. It says that we have an undefined class A2I. And the reason is we didn't supply the code for A2I. So if we look in our directory here, we'll see I've already copied in the class file for A2I, and I encourage you to go and look at that code. It's actually interesting code to see how the conversions are written in Cool. But now we need to talk about how to compile a program that uses a library. And the way you do it is very simple. You just list all the class files on the command line when you call the compiler, and it will read them all in and treat them as a single program. So in this case, we compile fact together with A2I, and that compiles. And then we can run it. And now, if I type in 3, it prints 4. And if I type in 1, it prints 2. And so the program seems to be working. And now we're almost ready to write our factorial function. So what do we want to do in factorial? Well, we want to do something other than just adding 1. Instead, we want to call our special function factorial. So let's insert a call to factorial in here. Okay. And let's get rid of the +1. And then let's check that we have all the parens that we need. So we need to close off the A2I call, the factorial call, the I2A call, and then that last one should be the outstring call, and it is. Okay. And so now we can add a method fact to this class. And fact is going to take an integer argument. So we need a parameter here, and its type is int, of course. And the whole thing is going to return an integer. And then we need a body of our function. And probably a good idea here, just to make sure that we got this much right, to do something simple. So let's just try to make a function that returns 1 more than its argument. So this will do exactly the same thing that we had before. And let's just confirm that that is working. So we compile with the A2I library, and now we have a syntax error. And we see that I forgot the closing semicolon here for the method. Remember, the class body is a list of methods, and each method is terminated by a semicolon. Let's try compiling that again. Now it compiles. Let's run it. We type in 4, it gives us back 5. All right, so it looks like we're ready now to actually write the code for factorial. And this is going to be anticlimactic because it's actually very simple code if we write it recursively. So let's do that. So how is that going to work? Well, everybody knows the definition by heart, I hope. If I is equal to 0, then the factorial of 0 is 1. And we need a keyword there, then 1. Otherwise, the factorial is going to be I times the factorial of I minus 1. Right? And then if statements in Cool always end in the keyword phi. So it's an if then else phi construct. And that is actually the entire definition. So now we should have a program that actually computes factorial. And it compiles. So now let's run it. So factorial of 3 is 6. And factorial of 6 is 720. That looks right. And if we try it one more time with a bigger number, we get a large number. We think that's probably correct. And so anyway, our factorial function is working. So now let's come back here, and just as an exercise, let's rewrite this code iteratively. So instead of using a recursive function, let's write it using a loop. And in order to do that, I'm going to get rid of that code. What are we going to need? Well, we're going to need an accumulator here. We're going to need a local variable that we can use to accumulate the results of the factorial computation. And the way you declare local variables in Cool is with let statements or let expressions. So we're going to have, let's call this variable fact for the result of factorial. And notice here that I can have a variable that has the same name as the function. And the programming language Cool will not get confused about that because variables and functions play different roles. So we'll have factorial fact, it's of type int, and we need to initialize it to 1. All right, so that multiplication will work. I think the default for integers is to be initialized to 0, and that would not be good if we're going to be multiplying up fact with other numbers. All right, so then a let has two parts. It has the variable or variables that you're declaring. This could actually be a list of variables. We only have one this time. And then it has a body, the expression or the computation in which the fact variable is available. And what do we want to do? So I think we're going to need to have this be a statement block, because we're going to need to have more than one statement in sequence, and we'll see why in just a minute. But then we want to have a loop. And so what is our loop going to do? Well, we're going to say while I is not equal to 0, what do we need to do? The opening for the loop body, the opening keyword is called loop. And now I think we're going to need another statement block here. So let's open up a block. We're going to probably need to do more than one thing. The first thing we want to do is we want to have fact be fact times I. Okay, so we know that I is not 0, and so we need to multiply the current value of I into fact to accumulate the result. And then we want to subtract 1 from I. And notice that the assignment statement in cool is this backwards arrow. That's how you do assignment. It's also how you do initialization. So initialization and assignment look the same. And then we can close off our statement block. Okay, so the body of a while loop is always a single expression. In this case, that expression is a block that consists of 2 statements. And then we can close the loop. And the closing for a loop is the pool keyword. And then now we're in a statement block, so this has to end with a semicolon. Notice the statement block up there from the let. And now we want the result of the let block, or the let expression, to be factorial. So whatever we got out of the while loop, whatever we computed in the while loop, we want that to be the result of the entire let expression. So that's the last statement of our block. Remember, the last statement of a statement block is the value of the block. The body of the let is the result of the let, so fact will also be the result of the whole let statement, since it's the result of the statement block. And since the body of the factorial method itself is just the let expression, fact will be the result of the whole thing. And so this, if we've haven't made any mistakes, should be an iterative version of factorial. So let's compile this. And amazingly, it compiles on the first try. And now let's run it. And whoa, it actually works. So we got 6. And let's just do one more test to see that, to convince ourselves that things are working reasonably well, and they are. Now let me just point out one common mistake that you can easily make, and that I make when I haven't written cool programs for a little while. If you're a C or programmer or a Java programmer, you might think about writing assignments like this. So you just use the equal sign to write assignment. That looks completely fine if you're familiar with those languages or used to programming in those languages. And now let's see what happens when we try to compile this. Oh, it compiles just fine. And then what happens when we try to run it? Oh, well, it runs, asks for an input, so let's give it an input, and then we see that we run out of heap. And that looks like an infinite loop. So we're going around and around the loop and consuming memory for some reason, and we'll get to that much later in the class, why this loop actually ends up consuming memory. But clearly we don't have enough memory in the loop, and eventually we run out. And so that's a sure sign of an infinite loop. So what's going on here? Well, the thing is that the equals operator in cool is the comparison operator. So up here, so we compared I with 0, and that returns a Boolean. So these are perfectly valid cool expressions. They just happen to be Booleans. And so you don't ever actually update I or factorial in this program. You're just comparing fact with fact times I and I with I minus 1. And the program is perfectly happy to do that. It just doesn't compute the factorial function, and it never terminates because I never reaches 0. So that concludes our factorial example, and we'll do one more example next time of a more complicated, of a cool program with some non-trivial data structures. Hello again. In this video, we're going to wrap up our overview of cool with one more example of writing a cool program. For our final example, let's look at a program that actually manipulates some interesting data structure. So we'll begin here by opening up a file, and let's call our program list.cl this time. And as usual, we'll begin by writing our main routine and our main method. And once again, let's make this inherit from IO so we can do the IO routines here. And let's just begin with something very simple, as always. Let's just have something that prints out hello world, but in a little bit of an unusual way. We're going to end up writing a list abstraction, and let's first build a list by hand, or at least build the elements of a list by hand, and then we'll actually build the list abstraction and put them in a list. So let's have some strings. So we'll have our string hello, and this will also illustrate how you do multiple let bindings simultaneously, and I shouldn't say simultaneously, how you do multiple let bindings in one let expression. So you do them by just listing them, and notice that this uses commas as a separator rather than semicolons as a terminator. So this let binding is going to define three names, hello, world, and new line, all of which are strings. And then we're going to now print these out on the screen. So we're going to want to be able to do outstring, and since main inherits from self, we can do that without an object there, because just again dispatches to the self object. And we want to concatenate these strings together in the right order. So we'll do hello dot, and since hello is a string, it can be concatenated to world, and world is a string, so it can be concatenated to new line, and that should do the job. And just let me point out one more thing about this these let bindings here. This notice that the comma is a separator here, meaning it doesn't come after the last one in the list. So it just separates the items of the list. It's not a terminator. And now we can close up our main procedure, close up our class definition, save it, and now let's see if it compiles. Oh, amazing. First try. And we run it, and it prints hello world as expected. So now, let's, instead of introducing the three strings separately and then concatenating them together, let's write an abstraction where we can build a list of strings, and then that abstraction will have a function within it to do the concatenation. All right, so we'll have a class called list, and every list needs, I think, to have two components. So first it's going to have the item that's in the list, and that'll be a string. And then we have a pointer to the next, to the tail of the list, to the rest of the list. And so I'll have a next field that points, or is another list of strings. And now we need a couple of methods in order to use this list. We'll need to be able to initialize a list in some way. So the initialization function will take an item and the rest of the list, the next part of the list. And what is it going to do? Well, it's going to need to set the fields of the object. And so this will have to be done as a series of assignment statements. So we'll need a statement block. And we will set the item to be the I argument. We'll set the next attribute to be the N argument. And now we actually want this initialized object here, this method here, to return the object itself, and that'll be convenient for chaining together calls to init. So we'll have it return self. It'll return the self object, and that's the end of our statement block. And then that is the end of our method. And made a mistake up here. we have to declare the return type of init, and what it's going to return, of course, is it returns an object of type list. We need to put a list declaration there. All right, so that takes care of init, and now we can use this to build a list down here. So what should we do? Let's actually have a new variable called list that we'll introduce here in this this series of let bindings. And let's just build a list out of these three objects. So we'll say we'll have a new list, and then we'll initialize it to contain the string hello. And what should the rest of the list be? Well, that should be another list, which is initialized to have the string world. And what should be inside of that list? Well, there'll have to be another new list object, which we'll initialize to have new line. And now, what do we put here? Actually, there's a little bit of a problem here, isn't there? We need to put a list object here, but we don't want to allocate a new list object. We want that to be really the equivalent of a null pointer. And there's no name for that in Cool, actually. You can't write down the name of a null pointer. It's called void in Cool. There's no special symbol for that. So we'll have to create a variable that is just not initialized, and that will be, so an uninitialized variable of type list will in fact be void. It'll be a null pointer. So let's call that nil, and it'll be of type list and no initializer. And so nil there will point to nothing, or the void pointer, and then we can use nil to terminate our list here. And then we have to close off all the parens for all the nesting here. And I think that's it. And so that will be our list. Okay, so we have a list of 3 strings. And now what we want to do with that is to print it out. And so what we would like to do is to have a list call to list, and then a function that's going to flatten that list, and we'll just print it. So that is what the main program should do. And now we have to write the flatten function. So flatten takes no arguments, and it's going to return a string. It's going to return a single string. And flatten is a pretty simple function. What do we have to do? There's really 2 cases. One is if we're at the end of the string, and the other is if we're not yet at the end of the string. So let's test for that. So how do we know if we're at the end of the string? Well, if the next pointer is void, then there's nothing more in the string. And there actually is a special test for that in Cool. It's called the isVoid function, and it's written like this. So if isVoid of next, okay, so of the next field. So if the next field is void, then what are we going to return? Oops. Well, then the result here is just the item, whatever the item was in this last element of the list. And otherwise, what do we want to do? Well, otherwise we want to take the item and we want to concatenate onto it the result of flattening the rest of the list. And that is our flatten method. So let's see if that works. So let's compile this. And we got a couple of syntax errors here, so let's go back and see what's going on. So we have a syntax error here at the end of the flatten method, and we see that we left out the keyword to close a conditional. So a conditional has to be ended with fee. All right. And let's see if that's working now. And we still have the syntax error at line 29. And the mistake here is that we forgot to declare the type of this variable, which is a list. And then it gets initialized to this big expression that we wrote out. Let me just do the indentation a little more nicely here. And notice something actually is worth mentioning here, that this definition here, this definition of the variable list, depends on the definition of the previous variables in the let. So so when a let binding is made, the name, the variable that's bound, is actually available in subsequent let expressions. So in this case, this variable list makes use of all of hello, world, and new line, which were defined earlier in the same let construct. All right, let's save this and come over here and compile it. And we see we got another bug in the code. So if we come up here, we see I've made a mistake here. I've used functional notation here, calling flatten of next. And what I actually wanted to do was to dispatch to next on the method flatten. So that should be written like that. All right, probably getting close now. Let's see if it works yet. Well, it compiles. And now let's see if it runs. And indeed it does. Prints out hello world just as we expected. Now let's go back to our program and let's generalize this list abstraction in one way. Let's say that we can have an arbitrary list of objects, not just strings. And that will require us to change a few things. So it can be initialized now with an object. And now when it comes time to flatten this list, we want to produce a string. We want to produce a print representation. But not everything in the list is necessarily a string. And we need a way to traverse the list and do different things for different kinds of things that might be in the list, for different types of things that might be in the list. And so there's a construct in Cool for recovering the type of an object at runtime, and this is called the case construct. So let me first introduce a let expression here. We'll let the string that we're going to construct, which is of type string, and that's going to be initialized to something. And now it's going to be a case. And what are we going to case on? Well, it's going to depend on the kind of thing the item is. So the item in the list could be different kinds of types, and we want to do a different operation depending on what item actually is. So we'll do case item, and then the keyword is of. And now we have different branches of the case expression for different kinds of things that could be in the list. So let's say if it's an int, okay, so what this does is this says that if the item is an int, then we're going to rename it to I. We're going to bind I to that integer, and then we can do something with I. And what would we want to do with I? Well, we'd probably want to convert it to a string. So I'll do I to a of I. And what if in fact that item happened to be of type string? The item in the list happened to be of type string. Well, then we can just use the item itself as a string representation. And we could do this for other kinds of types. If we had other kinds of types in our system, we could continue to list out other cases here and how to convert them into a string representation. But let's just have a default case here. We'll say if it's any other kind of type, which would be covered by having a branch saying that if it's of type object, and we'll call it O, then we should just abort. Okay, so we should just call the abort function and quit. And that's our case. It needs to be terminated with a closing keyword called esac, again, the reverse of case. And now we can use that string that we constructed in our little function here. So if the next field is void, then we're just going to return the string. Otherwise, we're going to return the string concatenated with the flattening out of the rest of the list. Okay. Now there's a couple of things we have to fix up. We use the I to A method here, which means that list needs to inherit from the conversion class A to I. And there's another issue here, I see, and that's right here. So if you notice, the case statement needs to produce a string, okay? And it turns out that abort does not return a string. Abort actually terminates the program, but its type is that it returns an object. And so here we have to convince the type checker to accept this piece of code, and we need to get this branch here to type as a string. So what we can do and this is ugly, but it's the way to do it, is we put it in a block, in a statement block. We call abort first, and again, that will just terminate the program. And now we can put any string expression we want after that, and that will be that will give a type string to the entire block. So we can just put the empty string here, for example, and that has to be terminated with a semicolon since this isn't a block, and we can close that with a curly brace. Okay, so this is just something we have to do to make the type checker happy. And that may be everything we needed to do. So let's try compiling this. And we have to include the conversion library. And we have one syntax error so far. And that's because we forgot to put the semicolon terminator on each of our each of the variables that we were introducing in the let. Okay, forgot to save that. Let's try this again. And oops, I didn't actually manage to fix the syntax error, and that's because I put the semicolon in the wrong place. Actually, I forgot the variables that are bound in a let are separated by commas, but the branches of the case have to be terminated by semicolons. So what I said before was incorrect about using semicolons to terminate let bindings. It's just in case branches in this where we need it in this example. All right, anyway, coming back to this, let's see if it compiles, and it does. And now let's run it, and it works. Now, of course, we haven't actually exploited the ability to have different types of objects in the list, so let's do that. Let's add an integer in here. Type int, and let's give it the number 42. And we can insert it in here. And now we can pass any object to a init in the first position. So we'll just put in 42 right there. And when we compile and run this, it should print hello world 42 if everything goes as expected. And it does. And that concludes our little tour of Cool. There are a few features that we haven't shown in these examples, but you can look in the examples directory for lots more programs, many more programs that will show you all the different ins and outs and details of the other language features, as well as the ones we've covered here.